Suppose that I have a solid, piece of solid here. Now just for example, let's say this is a piece of ice. Must be quite cold. Let's say the temperature is -5 degrees Celsius. So this is my piece of ice. Now I want to use a simple kinetic model to explain the melting and the boiling of this ice and then water. Now what simple kinetic model mean is just to explain it in terms of the movements of the molecules. So that's what this means. Means in terms of movements of molecules or the atoms. So what, as I said, what I like to explain is the process of melting and boiling. In order to do this, we can make use of what we have learned from the kinetic theory of gases. Now it all started with people trying to figure out what heat actually is. Right? What heat actually is many years ago. Many hundreds of years ago, in fact. And there were many ideas about what heat is, and the usual idea is that heat is some kind of an imaginary fluid that appears when things get hot and that flows around an object, and maybe it can go from one object to another. That's how heat gets transferred. Now later on, with the theories, the kinetic theory of gases, about using atoms and molecules to explain pressures and volumes and relating the energy of the kinetic energy of the molecules to temperatures of gases, it has been possible to explain many experimental observations about gases just by assuming that the molecules only have, just by assuming that the body is made of molecules and the molecules only have kinetic and potential energy. So that understanding from ideal gas and its kinetic theory allows us to apply the same idea to solids and liquids. So this means that heat is no longer something mysterious. Heat is nothing more than the movements of the molecules. So when things get hotter, it just means that the molecules move faster, or in a solid that they vibrate more with a bigger amplitude. Okay, so what do we want to explain about the melting and boiling? Now there are a few specific things that I want to explain. Let me start from the first one. Explain melting and boiling at constant. Okay. Let me make this clear. But why? I want to explain why they happen at. Okay, let me put it in a more obvious way. I want to explain why temperature, right? Why temperature stay fixed. So that means if I look at a piece of ice and it melts, while it melts, it will stay at 0 degrees. The temperature stay fixed all the way until the ice has melted. Until the ice has melted, then temperature increases. Now you may say that, right, that can't be right. If this ice melts, surely the water drips down onto the table, and that must be warmer. The water that drips on the table must be warmer, and maybe inside the ice, okay, maybe it's a lot colder. It could be a lot colder inside the ice, but on the surface of the ice it might be 0 degrees, and then the water that has melted would be and fallen on a table would have a higher temperature, might be a few degrees. So maybe it's just at the surface where the ice melts that the temperature stay fixed. That's one way to look at it. We still have to explain why it stays fixed. And just to make it less ambiguous, less confusing, I am going to think about getting a cup or a big bucket, and I'm going to put in these ice cubes, these little blocks of ice in the box, in this bucket. Okay, and as the ice melts, there would be some water that starts to collect. Okay, so now that I have everything together in the same container, in the same bucket, okay, the ice and the water, because they are so close together, would actually stay at 0 degrees while it melts. It would actually stay at a fixed temperature. And then after the whole thing has melted, it would then start to warm up. So this means that if I imagine plotting a graph of the temperature of ice against, say, time. That's time and that's temperature. In okay, I'll do it in degrees Celsius here. Then let's say that's 0 degrees Celsius, and let's say I start with a bunch of ice that is at -5 degrees Celsius. Maybe that's -5. Okay, so at first, the temperature will be -5, and then after some time, as I put this bucket in the room, the temperature warms up. No water yet because it's still below, and then when it reaches 0 degrees, it starts melting. So as it melts, there will be some ice and some water, but the temperature will stay the same, and I mean really, really exactly the same while it melts. As long as there's some ice left, right, it will stay the same. You can it is always possible that the part of the water that touches the side would be a bit warmer. Okay, but here we are assuming that if you shake it and keep stirring it, okay, it will always stay at 0 degrees Celsius as long as there's some ice. Now it's only after all the ice has melted, that the temperature continues to go up, and it warms up to room temperature. And the same story is true, right? The same story is true when it boils. When this temperature reaches the boiling point, after it reaches room temperature, I keep on heating it until it goes to 100 degrees Celsius, okay, then you'll start boiling, you start bubbling, and then steam comes out. Now, as it boils, the temperature is once again going to stay fixed at 100 degrees Celsius, right? As it boils and changes to steam, it's going to stay fixed. And only after all of it has changed to steam, then if you collect the steam and continue heating the steam, then the steam temperature would continue to go up. So at melting and boiling, temperature stay fixed. The question is why? Why does temperature stay fixed? And the reason is quite simple. Using what we understand from the kinetic theory of gases, right? We understand that the energy, the internal energy, which I have been calling U, is equal to the sum of the kinetic energy and the potential energy of the molecules. So the kinetic energy comes from the movement of the molecules, potential energy comes from the attraction between the molecules. Now, when ice turns into water, so that's during this melting phase, when ice turns into water, what happens? What happens to the kinetic energy and potential energy? Well, the potential energy depends on distance between molecules. This depends on the distance between molecules. Because it's about attraction, right? It's about attraction. So if distance is bigger, there's less attraction. It's like gravity. Okay, and kinetic energy depends on velocity. Right? This depends on velocity. It's half mv squared. Half mv squared. Since m doesn't change, it depends on velocity. So whereas potential energy depends on distance. Now when ice turns into water, there is not much change in distance. The water molecules are still in contact. They're still touching each other. But there's more motion, right? Once it turns into water, they can move around more freely. So we would expect that there would be increase in kinetic energy. There will be some increase in kinetic energy. Now, but for the potential energy, actually, let's see. Right, it's not really true that there's not much change in potential. In order for them to be able to move around, the molecules have to be able to move apart. Right, at least those that in the ice that are at first next to each other, they must be able to move apart. And in order to move apart, there must be energy to overcome that attraction. And that's what happens during the melting. During the melting, the water you can either warm it, or the water will absorb heat from the surrounding. And this heat will be used to pull the molecules apart. Okay, so rather than to increase the kinetic energy, and it is the kinetic energy part that contributes to the temperature, as we understand from this contributes to temperature, as we understand from the kinetic theory of gases. More temperature, more motion. So that's roughly true. So because the heat taken in is mainly used to pull the molecules apart, they are not used to increase the kinetic energy. All right. So therefore, the temperature stays the same. The temperature stays the same while it melts. And in the same way, during boiling, the energy is needed to pull the molecules apart so that the water can turn into steam. Because in steam, that's a gas phase, the water molecules are very far apart. In water, they are touching each other. So obviously you need a lot of energy to pull it apart. Alright, you need a lot more energy, than when it's melting. When it's melting, you just need to pull it apart a little, and then they can move around. But when it's boiling, you need to pull them apart a lot. So you need a lot more energy. Right? This also explains why you need more heat to boil water than to melt the same mass of water. Okay. So during boiling, all the heat would therefore be used to overcome the attraction between molecules. So we can imagine that there are these molecules and you need to pull them apart. So because there are attraction between the molecules. So that's what happened during melting and boiling. Okay, so the heat increases the potential energy, right? The heat is needed to pull molecules apart. So this increases the potential energy. It does not increase the kinetic energy. So therefore, temperature stay fixed. So this essentially is the explanation for why temperature doesn't change during boiling and melting.